Well, if you're watching this video, I'd like to thank you in advance. This is going to be a pretty boring video, but I need some help on a very technical topic. So the main problem I'm having is I want to develop a tool which will allow a user to select points on an image and have that image aligned. So for example, points here and then points in 3D, where after enough reference points have been selected, the user can then solve for a camera that when viewed from the camera, this image will overlay perfectly the 3D scene. Okay, so this is not a super new or exciting problem. I think this happens for almost every frame of the camera tracking for video in Blender, but there's no good way to do this for single images that I know of. Also, this problem is not new. It's been talked about a lot on the internet. So first, I'd like to just go over what I've got here in this test blend file, which I will put a link to this file in my YouTube description or in the video description. So I'll maximize this. In this file, there's an image called Lego OpenGL. This image was rendered with this camera, test camera, of this object, Lego Man. So this gives us a known data set where we know all the properties of this camera. We have an image which corresponds exactly to this camera setup, and it is of this exact object. So the only thing I did is change the materials here so that when we're looking through the camera, I can tell when the background image is on or not. Okay. Also in this blend, there are several scripts. Okay. The runme script is what will register this function that I demonstrated here, register image to object. That's the user interface that allows selecting of points in the 3D view with raycasting, and also pixel points in the image editor. Okay, link to the code for this will be placed in also the description of the video. Okay, and what you'll want to do is copy this file into your modules, and then because it's a part of a bigger project of mine, I import it like this. But once it's in your modules, you'll just change that to import this module, and then when you register it, it registers the Blender operator. Okay, so part of the algorithm that we're going to use, first let me make sure I hit all my points here. There are a couple other scripts in here that I will, and these instructions don't mean anything, but there are a couple other scripts that I will show in a moment. Great. So also in the video description, I will include a link to the Stack Overflow question specifically related to Blender. And this is another user who wrote this. And then my brief response is down here. Also, all of these links can be found in the header of the Python module that can be found in the link of this video, or in the link to which can be found in the description of this video. Okay, so let's go over the published algorithm, which I think most of these answers reference this book right here. Okay, so here is a Columbia Computer Science project from 2002 that describes the exact thing that we want to do and how to solve it, how to set up the set of matrix equations, the technique to use. Okay, and then this description is basically this exact same exact same answer with some mild differences, but it goes a little more in depth about factoring out the projection matrix and how you arrive at these sets of equations. All right, but basically what we do is we acquire our set of matched coordinates from the user. We then assemble this set of matrix equations, of which we end up with 12. Right. We then take the singular value decomposition of this large matrix that we construct. Given that deconstruction, we use eigenvalues and the eigenvector to reconstruct the projection matrix. And then once we have the projection matrix, we go back and make a Blender camera. Okay, so first thing I'd like to do is verify that our input data is good, that I don't have any errors on the user interface side. So what I've done here is when you click in the 3D view, okay, because we have this known camera here, first we raycast the scene and get a 3D vector. Then we use our known camera data to calculate what the pixel coordinate should be of that point. And that's wrapped into this little function here. And this function came from this user on Stack Overflow, and in several of his questions and answers. And it was, I think, originally derived from a different one, which he's actually included the link here. Okay, but the point is that because we have a known camera with known properties, we should be able to know what the pixel value is ahead of time before selecting them on the actual image. Okay, so I will print out those pixel values each time the user clicks. And our reference, the origin of the pixel coordinates is at the top left corner, so this is 0, 0. This is x max, y max here. So within a couple pixels, because we're rounding and the accuracy of the user, these numbers should match up. Okay, and they do. Okay, the next step is I want to jump to the end where we reconstruct the Blender camera from the projection matrix. So to make sure that that is working, jump down here to the camera matrix test. Okay, and these algorithms come from the same user, Dr. Fabry, who hopefully is watching this video. So he has several posts about deriving the projection matrix from a camera and going backwards, making a Blender camera from a projection matrix. So in the code that was posted here, I've included that in this module. And so this little script finds the test camera, calculates the projection matrix from that camera, and then builds another camera to match it. Now it doesn't match perfectly, but the point is that when viewed through the generated camera, the image overlay still works. So the camera's entire matrix is built up of intrinsic and extrinsic properties, and they combine together to make the total projection matrix. So as long as the total projection matrix is the same, it doesn't matter if the two components that combine are different. So let's just run that. So here's our new camera. Now it's the active camera, and indeed the image overlay looks the same. And let's just make sure that that is the active camera. Yep, there we go. Okay, so I'm confident that the back end of this code should work. So that I think we are done. We can be sure that we're in good working order here, and we're sure that we're in good working order there. So we've done this, we've done this, we've done this, we've done this. So now it's time to kind of investigate the middle part of the code here. For the moment, we don't need Blender. We need the approach taken and the matrix math descriptor. And all this happens in the function build matrix. Right. So the first thing is we need at least 6 known points. Okay, so first we verify that we have 6 points in each side. If we happen to have 7 in one or 8 on one side and 6 on the other, we take the most overlap possible and build our 2 lists of points. Now, in this answer, it does not mention scaling and centering the data, whereas in this answer, or in this approach, they do. So I have tried both ways with centering and scaling, and what they recommend is scaling so that the centroids are at the origin, and then making it so the distance to the center are root 2 and root 3. Okay, so that is everything that happens right here. So this text block, this code block corresponds to this text block, which is not included here. So this is one area where I'm curious if I'm doing something wrong. Okay, the next one, the next spot where I'm wondering if I'm doing something wrong is in the homogeneous coordinates. If I should be doing this after I've created my homogeneous coordinates. And that's actually something I have not tried. It kind of just occurred to me right now. So as we're going through our pairs, we're going to build a system of equations. I believe all this at face value and arrive right here to kind of the answer, so to speak, where for every corresponding pair we build one of these matrix equations. They claim here that the third row is just a linear combination of the first 2, so it doesn't add anything to solving the system, and so you just ignore it. So for every pair of points, you get a 2 by 12 or 2 1 by 12 rows, and you stack all 6 pair of those into a 2 by 12 matrix. Okay, so here are my 2 rows. So for every pair we have, here's where I calculate my 2 rows, and I've gone through and made sure that all this matches, and I understand what each component is, not just matching the letters to the letters. And then we stack those rows together. I have some printouts here to verify that the first row of my list of rows matches the first row of the NumPy array. Right? Then it talks about how to solve this matrix equation. Ignore the trivial answer, and it says use SVD. Take the eigenvector corresponding to the smallest eigenvalue, and that just happens to be the solution for the camera matrix. And so you unpack that and restack it up and form P. And so that's what I do down here. So here's the NumPy SVD function. It gives us these 3 arrays or matrices, depending on what your input value is. And it claims that the eigenvalues, or the square root of the eigenvalues, are stored in S. So you pick the smallest one, and then the row of V is the eigenvector. It also says that the columns of U are eigenvectors of a different, depending on which solution you want. And I'll be honest, I don't fully understand the difference between these two. So when I get down here, you notice I'm just trying a bunch of things randomly using the eigenvector from the V matrix or the U matrix. But in any event, when I'm solving these in our test scene, most of the values of S get very, very small, like practically 0, for over half of the 12 eigenvalues. So I've been told that that means something about our system of equations. So let's do one to completion here. Okay, and in this utility, you hit the M key to calculate the matrix, to do the matrix math, and hit escape, and it's done. And this will add a camera into the scene, wherever it is, and if you hit 0, it obviously does not line up. Okay, but if we come over here and read this, that's a bummer. Alright, we see that there's a ton of zeros in here, which is not very useful for building a camera matrix. And if we build it from U, it just gives us a nonsensical camera. And finally, if we look at the eigenvalues, the first 3 values seem reasonable, and then they quickly decay to being very, very, very small numbers, the final of which is 0. So somewhere in here, either in where I'm making my homogeneous coordinates, or maybe I'm not understanding how the NumPy implementation of SVD works, but I'm not getting results that I was hoping for. So thank you for watching. If you have any comments or suggestions, I'm all ears. And if you made it this far, you really deserve a medal.